This class is absolutely an introductory class. We assume you have no prior experience. Some of you do have experience in programming, but we assume that the students coming into this class have none. So we're going to start at the very, very beginning. So if you need help, again, I'm going to strongly encourage that you hit the CSX lab or you email me. Don't wait. If you're having a problem, don't go, oh, I'll just wait till next week and see if it clicks then. Don't do it. If you have a problem with this week's content, it's not going to get better next week because everything in this class builds on itself. The longer you wait to get something clarified, the harder it is for you to get caught back up. Does that make sense? And that's what we're here for. Ask me questions. There's no such thing as a stupid question. The only stupid question is the one you didn't ask me that shows up on your test. Yes, sir.
Is the face-to-face, is that walk-in or what?
Yes, you can walk in. You do not need an appointment for the CSX lab. If there's somebody in there, they will help you. Now we are going to get started talking about some basics. I'm going to be honest with you. I'm going to do very similar things to the textbooks, but there's going to be some stuff the textbook covers that I'm not going to cover. Doesn't mean that it's not important. It just means that I'm trying to use our time wisely. There also will be sometimes that I'll get a little bit out of order with the textbook, but that's just to move us along on some of the assignments. So there will be times when I say, okay, I'm going to talk about this, but we're going to cover it in depth later. Just go with me. It's very hard to do examples without using some of the stuff that comes later. So there's many different reasons and aspects of computer science. We want you all to become computer science majors if you aren't already one. So I'm going to try to talk you into that throughout the semester, especially if you're really good at it. Programming is just a small portion of computer science, but it's a building block for just about everything in computer science. Do you have to be a coder to be successful in an IT or computer science related field? No, but you need to have a general understanding of how coding works, because if you don't understand how programs work, it's really hard to block them when you're doing cybersecurity, things like that. So it's a building block for everything else. We're going to talk about programming from here on out. This is a programming class. We're going to talk about problem solving skills, because I can teach anybody to code, but teaching you to think like a computer programmer is a little harder. And it's not necessarily something intuitive. You went K through 12 learning to take tests and a learning style that wants you to memorize and produce from that information. This is going to be more of a computational thinking thing. We want you to have to think about how the pieces put together, deconstruct the problem, put it back together. We didn't teach you as much of that in your public education because we were more concerned with test results and judging whether or not your teachers were good at their jobs or not. I'm a former high school teacher. I can say that. So some project-based classes you had in high school in the last decade or so have moved towards that computational thinking kind of aspect. But if you're like me and you went to high school a very long time ago, this might be all new to you. We are going to be doing a lot of problem solving. Absolutely. We're going to have you put your thinking caps on. And to begin with, I'm going to lead you on the big project. I'm going to tell you exactly what to do. But as time goes on, I'm going to cut back on those step-by-step instructions and try to give you more nebulous ideas and see if you can come to a conclusion on your own. What we really are looking for is, can you break the problem down, come up with a plan of attack, and then concisely and clearly produce a result. And you've got to verify it works. Here's the real kicker in programming. You've got to test and test and then test some more, because it might work the first couple of times you ran it, but there's this weird, odd case out there that didn't work. I can't tell you in all of my years of degrees how many times I turned something in going, that works 100%, and then the professor found the one edge case that it didn't work for. And I'm going, oh, I didn't think about that. So be aware, test and test again, and then maybe ask one of your classmates to test it, because maybe they'll think of something else that you didn't think of. That'll be more important as you move further along into higher level courses. We're going to express solutions in a lot of different ways. One way that we might ask you to express a solution is in an algorithm. Yes, sir. Sorry. Forget how loud it gets out in the atrium. One way to express a solution is an algorithm. An algorithm is a fancy way of saying we're going to talk about our plan of attack in English or pseudocode or a mixture of the two and put it on paper before we start coding. And you're all going to go, well, why would I want to do that? And I'm going to repeat this throughout this entire semester. 30 minutes of planning with a pencil and a piece of paper will save you hours of frustration when you start coding. Promise you that taking a few minutes and getting organized on a piece of paper, whether that's drawing a diagram or writing out the steps you think you're going to follow, will save you hours of frustration in the long run. Because while you're doing that, your brain's processing it again, and it will sometimes it'll help you catch something you didn't think about and a step you need to add. It also will open up other possibilities for you. So just remember that. There are links in the PowerPoint to some videos about algorithms if you have a desire to learn more about the algorithmic process and things like that. I'm not requiring them. I just want you to be aware that that planning step is very important. I'm not big on giving you a formalized procedure for your planning and your algorithms. I'm not going to say you must do it the way I do it, because we all think differently. The way I accomplish a problem is not going to be the way you accomplish a problem. I've been told that I have a very weird way of looking at things, that I break things down.
Thought process.
Yeah, my thought process is off over yonder somewhere. You really want to ask my children one day if they're ever in here. They really don't understand me. Both of my kids are taking classes here at the university, so they will sometimes drop in. Or they'll call me and I'll put them on speaker and embarrass them. Because I like doing things like that. I'm a parent. All right, so what is a program? A program, in its simplest terms, is a sequence of instructions to tell the computer what to do. I don't care how many times you yell at your computer, it only did exactly what you told it to do. Makes you feel good to yell at it because it didn't give you the result you wanted. Completely get that. But I guarantee you the computer doesn't dislike you. It's not out to get you because it only did exactly what you told it to do. Why do we write things in code? Because we have to be able to translate it to the computer. There are a lot of terms that float around for people that program. Sometimes they're called programmers, sometimes they're called software engineers, sometimes they're called developers. And basically, they all do coding, but a software engineer or a software developer sometimes is going to be doing more of the critical thinking and problem solving. And they'll pass that algorithm or that plan down to a coder who's just going to implement the code. So it's like stair steps and levels of experience, really. You're probably going to start off as a coder. They're going to give you stuff to do without a lot of freedom to it. And then as you prove yourself to be valuable, they might actually take on more and more roles. Also, software engineers sometimes deal with hardware components. Developers and coders don't always want to deal with the hardware side of the computer science. I had a computer science professor back in my early days of my computer classes who once told the class that he can program your computer to do anything he wants it to do. How the hardware works, he had no idea. He told us that as far as he was concerned, there was a Kawada on a hamster wheel inside of his computer, making it go. For those of you that don't know, a Kawada is basically a South American raccoon type animal. I grew up on an exotic animal farm, so I knew this. But he didn't care. He didn't have to care because he was a programmer. My husband specializes in hardware and fixing hardware. So every time a software issue comes up in our family, because we fix everybody's computers, he hands me the phone, I fix the software issues. If it's a hardware issue, I hand him the phone and he fixes the hardware issues. Can we cross over and do both? Yeah, but our expertise is in different places. My expertise is in programming and networking. Those are my specializations that I took in computer science. He actually builds servers and his own computers and goes and changes out hardware components. I'm lazy, I just let him do it. All right, so programming languages. There are a whole bunch of programming languages out there. We're going to use Python. I have used more than a dozen different programming languages throughout my career. I am not an expert in those languages by any stretch of the imagination because I don't use them daily. Python and Java, I'm pretty good at. Used to be good at C++ and C, but I haven't used it in a decade. Not as good at it. The good thing is, once you learn the first programming language, the others come easier because a lot of the concepts are going to be the same. The syntax a little bit different, but the concepts will be the same. A loop is a loop is a loop. An if statement is an if statement is an if statement. So we're going to build. Why Python? Because it's an easier language to learn than some of the others. Studies have proven that it's a good jumping off point or a good starting point for a beginner program. Never going to ask you to memorize a direct definition, but if you want Webster's definition of a programming language, here it is. A systematic way of communicating ideas or feelings using conventionalized signs, and it's very wordy. It's a convention that we put together to take our thought process from English to computer code using this language in between. Because the computer hardware doesn't run on Python, it runs on ones and zeros and registers and switches and things like that. So the programming language is the thing that's going to bridge the gap between English or whatever spoken language we're speaking and the computer machine language. And yes, I have oversimplified that. You will learn much more detail about those things as you move into different classes that deal with that. But that's the overly simplistic way of thinking about it. I think I pretty much covered this. We're gonna the programming language takes the algorithm to machine code. It's more for us. Most programming languages are English based. Why? Somebody once told me, oh, it's because most of them are developed in the United States. No, because we're arrogant Americans and don't learn any other languages. But the majority of the world population speak English or know English as a second language or third language, or, Americans, we're the only ones that really only know one language. Sad, but true. I feel like these slides are redundant. So, like I said, there are thousands of different languages out there. We could take a survey, and I bet that somebody in here has heard of a language I've never heard of. I know I know languages that y'all have never heard of because I'm old and I don't use a lot of them. But, you've probably heard C, you've heard C#, you've heard C++, you've heard well, maybe not. You might not have heard of Fortran.
That's cool.
Fortran's cool for us old folks. Yeah. COBOL. We got Python, we got Ruby, we've got HTML is really a scripting language, but Perl. Gosh, just thinking about what I've written in PHP, they're all over the place. SQL, it's all sorts of languages out there. But like I said, you'll eventually specialize into something. Python is a higher level language or a high level language. It's general purpose. That means that it can cross platforms and be used in different applications. It's not specific. A lot of the older programming languages were designed for a specific function. Like Fortran was designed for specific scientific kind of functions. It's used in manufacturing and stuff a lot because it does calculations well. Java was probably the first multi-use language that came out, and that started in the 90s. As I was graduating with my undergrad degree, there was this new thing called Java that we learned in my senior year. But programming languages up until the 90s had a lifespan. It didn't stay the top of the heap for very long because there was always something new coming out. Python and Java are kind of breaking that because they've been the top of the heap for a while. Object-oriented programming has really helped a lot with that. You guys are so lucky that you don't have to do procedural programming, and you don't have to learn how to allocate and deallocate memory locations, and Java cleans all that up for you, and so does Python. You don't have to release and renew memory. You're not working with 32 megs of RAM instead of 32 gigs of RAM. You've got it made. There was a time in my career where you had to worry about whether or not your program was going to be using too much RAM at any given time, and you had to optimize your code. You made your variables as small as absolutely possible, and they didn't take up too much space, and you had to allocate, deallocate.
Sounds terrible.
It was terrible. It was terrible. But at the time, that's all we knew. The computer understands these languages because they use what we call an IDE, an integrated developer environment that will take the language and convert it to machine code. We're fixing to learn about that. So we have our source code. It goes into an interpreter because Python is an interpreted language, not a compiled language. You'll learn more about that as you move on. I don't know, the old book had some of the reading. You can, I'll get you some links if you're interested. It's just a difference in how they're packaged and they're run on the computer. You'll learn more about that in operating system classes and things. For our purposes, it's an interpreted language. So we write the source code. The idle IDE is going to convert it from Python to something the machine reads, and then the machine code is read by your processor and does stuff and gives you some sort of output. It does something. So let's talk about idle. So the IDE we're going to use is idle. It comes free from the Python site. You can go to python.org and download idle to any of your devices. It does not work great or easily on a Chromebook. Sorry. It is installed on all of these machines in here. I highly recommend that if you have your own device at home or you have a laptop, that you go ahead and install it there. It does not take up a lot of space. It's not a huge overhead program. It looks a lot like Notepad++ or something like that when you start looking at it. It's very simplistic looking, but when you type your code in, it does debugging and catches syntax errors and things for you. It does that interpreting and converting for you, that sort of thing. We're going to use the source code editor portion of it. We're going to run from there. It's going to build the program. I'm going to walk you through this stuff. So idle, like I said, is the name we're using. Let's go look at that real quick. Let's jump out of this. So on these computers, I just type in the search bar idle because it pops it up on the top. And it opens up with something that looks like this. Let me make the text bigger where you guys in the back can see. All right. So it opens up into what we call a shell window, which is fine for what we're doing right now. Later, when you're ready to save your stuff and you want to do it as programs, don't do it in the shell. Because it's the run window. It's what these are actually running. So like right now, I could type a single line of Python code and it will actually run it from here. Oops. If I could type today. So I put in a line and then it automatically, when I hit enter, it did it. That's not really writing a program. That's just a runtime environment. It's letting you test a line of code or a couple of lines of code. When we get ready to do our stuff, we're going to open up a new file and do it in a file where we can save it. Because you want to save your work and turn it in. Theoretically. Get it graded, get a good job. So this is the, like I said, this is the shell. And we're going to play with it today a little bit just to show you some of the commands and how they work. I need two screens going here. So the next chapter actually deals with variables and assignments and stuff in greater detail. But for the purposes of today, I'm going to gloss over them just a little bit where we can play with it. But if we wanted to create some variables, a variable is a name, location in memory that you can store something in. You could think of it like a moving box. When you're moving from house to house, you have a box. You could put an assortment of things into the box based on what size it is. And if you're smart, you have clearly labeled the outside of the box for when you get to your new home, where you know that this one contains kitchen stuff, or this one contains sheets, or so if your variable is clearly and usefully labeled, you will be able to find your data quickly, right? If you name it A, B, C, D. You may or may not remember what A, B, C, or D is 2 days from now when you come back to it, or 2 years from now when you come back to it. So clearly defined names are great things. So in this case, let's give you some examples of some variables. So if we're talking about a car, the make of the car would be a Ford. Name, if you're asking for somebody for their name, you would name that variable name. If you're doing just first name, you might call it first name. So these variable names need to be clear. I will harp on this every time you turn something in to me, over and over again, about variable names need to be clear and they need to be useful. When I taught high school Java, I had a student turn in their final project. All their variable names were Pokemon characters. This was great for him. Not so much for me because I know Pikachu and that's about it. But it made it very hard to give partial credit or find out where he went wrong with something because the variables didn't mean anything to me. So don't annoy me when I'm grading your stuff. The good news is that he also had another version that wasn't Pokemon characters, and when he realized he had annoyed me, he gave me the real version. But you know, high school, it's fun, right? So if we wanted to, we could use these variables in idle. I could go over here and do name equals good. And when I hit enter, it comes up with this. The icon is flashing, which means it's waiting for you to give me input. So if I type my name in here, it doesn't show me anything, right? But if I did use the variable name to print out, it goes and gets whatever in that variable. Does that make any sense? This is going to make much more sense when you start doing it yourselves. I'm just trying to introduce concepts today. Doing it in idle is going to look different than doing it in the web environment of your textbook also. So I'm going to mix it up. I want you to be able to do it in both places, but it's most important that you understand how to do it in IDE because you're not always going to have a web environment like the textbook to work from. And the textbook uses a slightly different formatting than it is. So we also, have what we call naming conventions. Python has rules for how they expect names to look like. So you can't have a space in a variable name. If you have a compound word or a 2-word variable name, you have to use an underscore. Please feel free to have multiple word variable names, but you have to use an underscore. If you use a white space, the IDE or the compiler, the interpreter, whatever you want to call it, sees that as, oh, I've stopped this variable name. What's coming next will be something else. White space means done with this particular stage, moving to the next stage. You should never start a variable name with a number or with an underscore. Just naming, this is a convention that we've all agreed to. We're not going to do it. You can spell out the number, but don't use the digit 0 through 9 to start off. It is absolutely more readable to use that underscore than it is to run class average together with no spaces and no underscores in it. Variable names always are lowercase. You will very, very rarely have something start with an uppercase letter because that means it's special and it does something different. So variable names are lowercase and they are divided up with underscores. Now, not to confuse the issue, but when you get to Java, it's done differently. They use camel case, so that's Java. So definitely have some naming conventions. I'm going to hold you to. Now, am I going to take off major points for you screwing this up? Not initially, but when we get to the last week of class, if you consistently broke all my naming conventions, I'm going to start hammering you for it because then you're just doing it to be obstinate. And if I teach you good habits now, it'll save you a lot of heartache later. We're also going to introduce something called comments as we move further along too. And beginning programmers hate writing comments for some reason. I have no idea why. So I will grade you on whether or not they have comments when we get to that too, because if I don't make it part of your grade, you won't do it. All right, so there's two different types of errors we're going to be encountering as we go through coding. We have syntax errors and semantic errors. The syntax errors are the easy ones because your IDE is going to usually catch those for you. You've misspelled something. You left some punctuation out. You used the wrong type of data. Those get flagged really quick when you either run it or you are typing and it underlines that you messed it up. The hard ones are the semantic errors. So these are your logic errors. This is where you type the code fine, but the logic you use to get from point A to point B went off the rails somewhere. You didn't put the formula in the right order. You missed a step, but your code's pretty. You're just not getting the result you thought you should get. Those are a lot harder to debug because it's kind of like an English paper or any kind of paper, paper you've written. When you read it, it reads okay. It says what you think you meant for it to say because in your brain, it's reading it that way. This is why you should always hand papers to somebody else to read, and they catch that there error where you use the wrong word. That sort of thing. Same with coding. I'm going to tell you this too, or I'll tell you this multiple times. If you are stuck on a major project and you've been looking at the same thing for 30 minutes or more, get up, walk away, go do something else. And while you're doing whatever else it is, whether it's the laundry or grabbing dinner, your brain will go, oh, wait, this is what you should have done. Then you can go back and fix it. But sitting there staring at the same 2 or 3 lines of code beyond 30 minutes is just wasting your time. You're just getting more and more frustrated. You need to remove yourself from that situation and come back. Or email me. If you've removed yourself from the situation and it still doesn't work, copy and paste some code or give me a screenshot, send me an email and say, I'm stuck. What did I do? And if I can help you, I will. Sometimes I need more than what you screenshotted to me, and I'll say, okay, send me your whole file. But as long as it's not 10 minutes before it's due, I will look at it and give you feedback. Yeah.
Where does that kind of error show up? If it's hard for it, again, you mentioned it's hard to see.
It doesn't show up until you run it.
And it shows
and your output is wrong. Now, the syntax errors are going to show up almost, some of them will show up as a typo, especially if they're, that you misspelled something.
Yeah.
Or they'll show up when you press run if it's a type mismatch. But the logic ones are gonna be your testing. It's gonna be,
The
because
output itself shows that.
you're gonna, that's the reason I tell you to test it frequently. And we're gonna cover that a little bit further in the slides, but we're gonna do what we call iterative programming. Iterative programming. We want you to do a part, test it, make sure that works. Then do the next step, test it, make sure that works. Because the instinct or the inclination for a lot of programmers, especially if you have a little bit of experience and think you know what you're doing, is to write all the code and then test it. And then you have a problem. Well, now you've got a screen full of code and you don't know where the problem is. Now you're just going to guess where you went wrong. But if you say you were doing a program to calculate the area of different shapes, if you do the square first and test it, make sure you're always getting the right area of the square. Then you do the section that does a circle. And then you do the section that does the pentagon or whatever. You can narrow it down if you tested it at each step where something went wrong. Because if it was working when you tested at step 2, but it's not working at step 3, then you know the code you wrote between these two places, these two testing points, is where you focus. And yeah, that was an oversimplification of things you probably aren't gonna.
If you do end up going too far, can you comment out and just like?
Yes, absolutely. I will strongly encourage you to comment lines out. I will also strongly encourage you to use what we call print line testing. I have honestly written code where I'm like, I have no idea where I went off the rails here. And I'll go in and go, works this far, print line, got you here, print line, made it to second step, and just put in these prints where they show up on my screen that I know that the code hasn't failed to this point. And then comment them out. When you're finished and 100% done with the code, you can go back and remove all of them and make it look pretty. And if you have something that is working, but you had a better idea, don't delete the code that's working for your, and then write your better idea. Comment that out, leave it there. Implement your new idea, make sure it works, because even if nothing else, you can go back to the less elegant code and have a working project, or at least a partially working project. Save and save often, especially if you're using the virtual lab or the computers in here. You need to have a USB drive to save to. These machines reset every night. Your code is gone.
Is your progress gone? Like if you do a lab or something, it says.
If you didn't save it somewhere off this computer, it's gone. Now, if you submit it to CourseDen, then you have a copy of it. It's in CourseDen. But if you just save it to the hard drive, it's gone. Gone. This is one of the reasons I don't like Google products. It leads y'all into a false sense of security because it auto saves. The real world does not auto save. The good news for you guys though is that the the compiler, every time you run it, it saves. It forces you to save every time you run a test. So if you're testing frequently, you're saving frequently. If you're just writing lines and lines and lines and lines and lines of code and you're not pressing save and you're not testing and the power flickers, you've lost hours of work. Don't do it. It's not worth it.
Everything with virtual lab, setting to be like access log out at a certain time, sit in a state as before.
I don't know. I have never actually used the virtual lab. I'm gonna be straight up with you. I've never had any reason to. ITS runs the virtual lab for the Python course. So theoretically, yes. In my experience, students lose a lot of work on the virtual lab because they don't realize they didn't save it correctly. Which is why if you have your own device, I would do it on our. We are going to be working with values. Values have types. Types is one of the chapters we're going to get to in chapter 3. And we'll go into great detail about it. But for right now, we're going to deal with 2 basic types. We're going to do numbers and strings. Numbers are broken down into whole numbers and numbers with decimal places. And strings are 1 or more characters. So strings often are indicated with quotation marks. Maybe single quotes or double quotes. Double quotes are more commonly used for a string because we like to use the single quotes for single characters. These are all strings. If you have the number 4 with double quotes around it, you have made it a string, not a number. Because my mailbox has 3 numbers on it. But I can't add those numbers to my neighbor's 3 numbers and get a viable result for the next mailbox. Because they're characters at that point, not numbers. Does that make sense? Okay, well, let's try it again then. So 2 plus 2 is 4 if they're numbers. But 110 on my mailbox and 184 on my brother's mailbox, that happens to be my neighbor, does not give me the house number for the next one because mailbox numbers are not based on math, right? They're based on distances. If you didn't know that, I'll be happy to explain that to you when I do. But that gives the EMS, firefighters, and other emergency personnel a distance. So how far down a road you are based on your mailbox number, especially if you live in a rural area like this. In the city, it's different. But we do use numbers for things other than math. When we're using a number for something that's not math related, it becomes a character. Phone numbers are not really to the computer a number because we're not going to do math on them. They're values that indicate how to find my phone. That's kind of really an address too. Does that make sense? Does that help? All right. So we need to be careful when we're doing this. If you get input from your user and they give you 4 in quotes, it's going to screw you up. And users do stuff like this all the time. I wish they didn't, but this is why we have to check them when we get input from a random user. There are some special characters that you will see through this program. The one that you're going to see pretty quickly is the new line character. And what that tells the computer is when you're formatting something that you want to throw text down to the next line, or you want it to only read until the end of the line. So that one's going to pop up pretty quick. We are going to spend some more time on stuff like this as we go through. But I didn't want something to jump out and it not make sense for you. If you are printing out and you need to print the quotation marks, because they are used to indicate strings and characters, if you just want to use them for formatting to print, then you have to use a special character for them in your print, which is a backslash and then the quotes. Or no, I'm sorry, forward slash because it's leaning forward. Forward slash then the quotes. Right? Like I said, all these PowerPoints are still out there for you. Numbers are going to be either integers or floats. Oftentimes integers will be abbreviated as INT, actually a lot of times, and we'll call them ints. Just like, well, when we get to characters, I'll stop calling them characters and I'll call them chars, because that's how they're indicated in the programming language, because old programmers were lazy and they truncated everything they possibly could. So a float means it's a floating point number, has a decimal in it. It has a fractional portion associated with it. There are other number types, but these are the two that we're going to use predominantly in this course. Integers mean that they are whole numbers. And programming languages, in my experience, do not round for you. So if you try to put a floating point number into an integer box, it is going to throw away your decimal place. It could be 5.99, and it's only going to keep the 5. There is no rounding. It does not automatically round for you. So if you need that level of precision, you need to make it a float. Now, can you put a whole number into a float? Absolutely. It just becomes 5.0.
When you say put into a float,
A variable, a type. You can force data types to change. Again, we'll get into that as we move forward. But sometimes you start off with integers, like you may have number of kids in a family, and then the number of families in your group, and you want to know what the average is. Then you might need to go, because kids are whole numbers. You can't have a fractional kid unless you're doing statistics for the census. Somehow it's 2.5 kids in a house. But if you start off with whole numbers, but you need the result of the math to be a decimal place, you can force that to happen. It's called typecasting, but we'll get there. We are going to see the print command a lot. Print is a built-in function. You have a keyword print, and then what you want to print goes inside of the parentheses. If it has quotation marks around it, it prints exactly what you typed. If it doesn't, it prints whatever's in that variable. That makes sense? So like when I printed name, I just put name in there, but it printed what was inside of it. So if I wanted to print my name, I would have put quotation marks around it. I think I'm going to pick up here with variable names next class period, because I think I've covered a lot. I think I've put a lot on your brain at this point. And we're not in a great rush. The whole next chapter is on variables and assignments. So we'll just ease our way that way. I do want you to go and look at the labs for chapter 1. They're due at the end of this week. Next class period, I'm going to actually do at least one of those labs with you, and I'll record it. And we'll do it in their environment. And then we may pull it out and do it in idle too, just for you to see the differences. But I want to do some actual coding with you. I probably will bring one of my old labs with me that's completely out of the book. And we'll do that together too in idle, because I want you to see how idle works. Questions or comments before I shut us down for today? Everybody's happy with me?
can I talk to you after class?
Absolutely, I'll be here. We technically have 15 more minutes of class. I'm not going anywhere. I just feel like I've been talking a lot, and y'all look like you're kind of glazed over on me, and I'd rather stop than you not get it. It won't be this boring as we get further into it, because we'll be able to do more coding as we're going. But to get us started, I have to do a lot of talking and a lot of terminology, and it even bores me. So